Hello everyone. Let's continue into looking different sources of variation. So the second source of variation is the oxide thickness. So let's begin with an inverter itself because this is a very good example to look into each and every attribute of a MOSFET. So when you expand this particular inverter, you'll have a PMOS and NMOS as we explained in the previous video. And when you try to open up any one of the transistors, you will see something like this. We are looking now into the cross-sectional view of the transistors. Initially, we saw the layout of the transistor. Now we are looking into the cross-sectional view. That is a transistor. So you have this gate oxide over here. You have the polysilicon or the metal gate. You have the P-type substrate. You have the source terminal on this and the N plus diffusion area. You have the N plus diffusion area and the drain terminal. So this is what a MOSFET looks like. And over here that you see, that is the gate oxide. So we are talking about an oxide thickness variation over here. So let's see what does that exactly mean. Okay, so before that, if you look into an inverter chain, again repeating the same thing that we looked in the last video, that inverter chain will look something like this with a flop which is present over here, or it could be a clock to clock pin of the D flip-flop and so on. So chain of inverters, the layout will look something like this. So what we'll do is we'll take one of the transistor, basically let's take this PMOS transistor and let's look into the cross-sectional view of it. Okay, so we have this transistor and we have this particular cross-sectional view of the transistor. So when you cut the transistor in this particular fashion, this is what you see. So just imagine try cutting this particular transistor from this point. So and try viewing it from this side. So what you will see is, you will see a polysilicon gate, which is this one. You will see an oxide beneath it, which is this one, and you will see the diffusion area, out of which one is the source and one is the drain, this is the source and this is the drain. Okay, so this is how your transistors looks like. So we are looking into the gate oxide. So in an ideal scenario, in an ideal case, the gate oxide will look something like this. In an ideal oxidation process, the gate oxide thickness will be constant throughout the channel. Okay, that's what is expected from an ideal oxidation process. But the ideal oxidation process, for an ideal oxidation process to happen, things should be ideal. The things around in the fab should be ideal, and that's not exactly the case. So we are looking into a real oxidation process. So there's a typo over here. We are actually looking into the real oxidation process. In that real oxidation process, if you see the oxide thickness is not constant along the gate length. It's very disturbing. It is I've shown the worst case. It could be better than that, but I'm just showing you the worst case, that the oxide thickness is not very constant, whereas it is expected to be constant across the complete channel length. Okay, and this is what you see in a real oxidation process. So what can go wrong because of this? And first of all, we are looking into a variation in the oxide thickness for one transistor of a single inverter. Similarly, you will have so many transistors. You will have a pool of transistors, out of which each and every transistor will show you this particular oxide thickness variation to some extent. Basically, the oxide thickness variation that you see, let's say for this transistor, will be very different from the oxide thickness that you see, for example, let's say for this transistor. So and that too, and the oxide thickness variation for this transistor and this transistor should be equal, but there will be still some variations. Okay, so this variation is there all across your transistors. And again, as we said, since the middle transistors are accompanied by another transistors, or middle inverters are accompanied by another inverters, so there will be very less variation seen over here. There will be a variation, but it will be a minimal. Whereas if you see the variation for the gates or the transistor which are sitting at the sides, there will be much more variations as they are exposed to other structures as well. Okay, so this is what you see. Now in this current equation, the ID is equal to mu Cox W by L. If you look into the oxide capacitance, which is Cox, that's dependent on the oxide thickness. And so this is how your drain current directly gets impacted from the oxide thickness. So the more the oxide thickness variation, more is the ID variation. And the next job is to identify how much is the change in the drain current affecting the CMOS inverter behavior. So let's try to look into this one and also do some smart simulation in the next video. Thank you.